Hi everybody. I'm making a video this afternoon to help you with homework 15. We are studying hypothesis testing this week. It's a challenging subject, and I thought rather than critique your homework, I'm going to actually show you some worked out video solutions, and I'm hoping that that will help you with homework 16, which is due on Friday. And I also hope that will help you guys in your performance on Monday's quiz on these two chapters. So let's get to work here. You have certainly done a lot of work this summer. And so this week, when we started this hypothesis testing, we had an introductory chapter, chapter 11, and we did homework number 14, all the exercises for that chapter. And now homework 15, which is chapter 12, I asked you to read the first 4 sections, A through D, and then to go ahead and try. There were 8 exercises, and so we're going to start those together with number 1 here. And I'm going to go ahead and work them out on paper and also show you how to use technology to do some of the computations. I'll try and show you the amount of work I'm looking for when you do these, and that can help you as you start the next homework assignment. So let's start with problem 1. It says the scores of a random sample of 8 students on a physics test are as follows. Okay, so we have 8 physics students take a test. And there's the numbers there over to the left. I could write them down, but I'm going to be putting them in a calculator or computer pretty soon. So part A says, test to see if the sample mean is significantly different from 65 at the 0.05 level. Okay, so we've been using this Greek letter alpha, which is the Greek letter A, lowercase a, to recognize, to represent what's called the significance level. And they say we want that to be 0.05, okay? So that's what's called the significance level. And we've also learned about something called the probability value, or p-value for short. And basically, if the p-value is lower than the significance level, then we reject what's called the null hypothesis. So there is the null hypothesis, and there is what's called the alternative hypothesis. So it's funny, I'm not really doing the problem yet, I'm just trying to make sure you understand the concepts from chapter 14 before I start working on the problem. Okay. And so we're going to have a null hypothesis, and basically the way these work is you have some parameter, okay? The way this works is you have parameter equals something, and then you have an alternative hypothesis, okay? So in our example, the null hypothesis, let's see. It says, test to see if the sample mean is significantly different from 65 at the 0.05 level. So I mentioned to you guys on the assignment, let me go back to the assignment itself, that it might be useful to use the Google sheet entitled Hypothesis Testing with One Population. So if I click on that, I get this. Now remember, to use these, you're going to have to make a copy. So if I click on make a copy, now I have a copy here where I can edit the sheet. Now, when you launch the sheet, you actually get these instructions, and you'll notice that there are several different worksheets after instructions. You have mean, sigma known, mean, sigma unknown. Sigma, remember, is the standard deviation of the population. Remember that Greek letters tend to be parameters. They have to do with the population. Okay. You can also find You can do hypothesis testing for proportions or variance or standard deviation. There's a few different things. The one we're going to use the most is this one, mean sigma unknown. It's very rare that you're going to know sigma. And I think when you do this, you're going to find a different set of data in here that you're just going to want to delete. You'll notice what I did. These data values are exactly the data values from number 1. There were 8 physics tests. And so what I did is I copied those here. And the reason I did so is because I wanted to know, when you do that, it computes the mean, the standard deviation, and the size of your sample. So I have 8 in my sample, and there's the mean. It looks like the mean score was a 69.1. This must have been a tough test. And the standard deviation was 6. Notice if I change this to a 30, the sample mean goes down to 65, right? And the standard deviation would go up a lot because that would be much more of a variety of scores. Let's put the 60 back there where it belongs. So there's the 8 scores that they gave me. And what I'm going to show you is how you can use this now to compute, to do a hypothesis test. So what I want to do next, let me move this out of the way. I want to go back to the problem and say a little bit more what they're asking here. There's always a null hypothesis, okay? So the null hypothesis would be that the average is 65, the mean. And again, when we talk about a parameter, we tend to use Greek letters. So the Greek letter M looks like this. It's the Greek letter mu. And so the claim is that the mean might be 65, okay? So in this case, the alternative hypothesis would be the mean does not equal 65. And by the way, I'm just going to mention, when you use this symbol, not equal, this is what we're going to call a two-tailed test. There is also a one-tailed test if you put a less than or a greater than there. But the null hypothesis has to have an equal to, or maybe a less than or equal to. It has to have something with an equals. And so I think that's important to understand, that the null hypothesis has to have the equality. Okay, so the question is it true that the mean equals 65, or is it possible that maybe the mean does not equal 65? Oh, a little bit more terminology. Sometimes the null hypothesis, we write H0. The German name for 0 is null, so that's sometimes, or naught. But anyways, the alternative hypothesis, sometimes people put H1 or they might put HA. Those are lots of things that are used in the literature. So we're trying to either say we reject the null hypothesis, or maybe we don't have enough evidence to reject that. Now, let's take a look at what we computed. I think this is important to remember. See, my sample mean is 69. That's bigger than 65. Are you surprised? Well, maybe not. I mean, maybe if we tested hundreds and hundreds and hundreds of students, maybe the mean would be 65. We just happen to have a better class than average. Or I should say these 8 students happen to be a little bit better than average, right? But maybe if we picked a different 8, maybe they'd be below average. But let's suppose I had a different set of data. Suppose you saw this for the scores. Right? And your sample mean was 95.5. And what if I told you that these students were randomly selected, but that the mean is 65? You may start to question my honesty. You might say, no, there's no way that you randomly picked 8 students. Maybe you picked the best students on purpose. Or maybe we reject the null hypothesis. Maybe we don't think the mean is actually 65. Maybe this test was easier than what you're saying. So that's the idea behind hypothesis testing is sometimes we get a sample mean that is so far away from what we claim the population mean is that we say, hey, that has to be wrong. That's when you reject the null hypothesis. And so the question is, are we going to do that or not? And the idea of when we do it comes down to this picture that you've seen many, many times, right? So you've seen this picture of this bell curve, okay? And the bell curve, of course, the normal distribution, or sometimes we use the t-distribution as well because the t-distribution looks a lot like the normal distribution. It's symmetric. It's just there's a little bit more data at the tails, right? Than you have, and the normal's a little more thin. We talked about that. So you have your mean, right? Maybe that's 65. And the question is, my sample mean, which your book calls M, some books use X bar, but you can use either one. Our book will call it M. That we computed, according to the computer on the left, 69.125, right? That's my sample mean. I think I should use X bar, otherwise it looks too much like my mu. So X bar is 69.125. And I guess the question is that possible? Sure, it's possible. I mean, is it likely? Yeah, it's actually maybe not too unlikely that that would happen. But again, if I had X bar equals 99.125, you know, if it's over here, or even, well, it'd be way out here, right? And you would say, hey, wait a minute, that's really unlikely. I don't think the mean is 65. So this is kind of the idea behind this. Okay. Well, it turns out that we have a formula that you've seen again and again. Z equals X minus the mean mu over the standard deviation sigma. That was our formula to convert a data value X into a Z-score. And you've seen that again and again and again. And there's a very similar formula in the book that I want to point out under tests of means. So I think I'm going to take you right to this. Well, maybe I'll go to difference between two means, even though we're not there yet. I just remember it has the formula that I think is really important. It's this idea right here. T equals statistic, kind of like my X value, minus the hypothesized value, notice that in our case would be mu, over the estimated standard error. So I'm just going to write standard error. This idea comes up again and again and again. It's actually one of the things I like about your book, is they make you realize that this same X minus mu over sigma idea is also used when you talk about the t-distribution. And so we're going to end up using that to compute a value of t, and then we're going to figure out whether or not that t value is far enough away from the mean that we start questioning things and maybe reject the null hypothesis. Okay, so this is the idea. So I need to compute t. Now, how does this work? Well, and again, maybe the place to go is right here. This problem, we are talking about a single mean, so this is section 2. And so let's scoot ahead a little bit. There's my formula again. The special case of this formula for a single mean is t equals m minus mu over s sub m. I think I'm going to write that down. So we're going to do t equals x bar is what I'm going to put instead of m, minus mu over s sub m. Now you might remember that we computed the standard deviation of the means, okay? And what this was the standard deviation that you get over the square root of n. And we studied this when we studied the central limit theorem. So maybe I'll put that in parentheses to remind myself what I need to do here. Okay? And so if I want to compute my statistic t to see where it is, okay, what I'll do, let's see, I have some of these values now. So the sample mean is 69.125. So in my case, I guess I could write down t equals 69.125 minus mu. What we do when we do a hypothesis test is we pretend we know the mean, or we pretend that the hypothesis is true. So that would be 65 if the hypothesis were true, right? Hypothesized value over the standard deviation, the standard error. So the standard deviation is 6.10474, but we need to divide by the square root of n, so that's the square root of 8. And if you calculate that, you will get the t value. Okay, so there's a couple ways to do it. I mean, I can pull out a calculator and do it, I guess, and I could work that out. But it turns out that this is programmed directly into the left side of this sheet. Okay, so they have some really nice things here. It says, what is your null hypothesis? Well, our null hypothesis is that the mean equals, and notice you can choose some other things if you have a one-tailed test, but we have a two-tailed test. The mean equals, and I will put here 65, because that's what our hypothesis is. The alternative hypothesis is that the mean does not equal 65, so that's the alternative. Okay. My sample mean that I computed was 69.125. So again, all these are coming from the right. The sample standard deviation was 6.10474. The sample size was 8, 0.05 for the level of significance. Notice what it does is it computes some things for me. It computes that the degrees of freedom, that's 7. Okay, well that's just 8 minus 1. We've had that formula before for the t. It says that the t-score is 1.91, and it also gives me the critical values. Okay, so let's draw a picture of exactly what's going on here. Okay, so here is the picture. This is, I'm going to draw a bell curve which looks like this. It's like the one up there, but what you just did is you made this into a standard t value. And so instead of the mean being 65, the mean of t or the normal distribution is 0. It tells me that the critical values are, if you look right below that where it says critical values, they go from negative 2.36 to positive 2.36. So I'm going to put those critical values here. So if this is 1, this is 2, this is 3, so somewhere around here is 2.36, and somewhere around here would be negative 2.36. And so what happens is, if my t value ends up being in that region beyond 2.36 or beyond, then we would reject the null hypothesis. But now if you look, I can click on this cell here, and you'll notice what it's doing. If you actually look at the formula, it says it's C6 minus D4 divided by, and not just C7, but C7 over the square root of C8. And so it's exactly doing this work that I filled here. And so whether you used a calculator or whether you let the computer do this, it looks like the t-score, the t value that we got, t-score is 1.911. Okay? And so on my picture, 1.911 is a little bit before 2. And so that is my t-score, 1.911. So what I would say is this is not significant. It did not fall into the critical region, okay, which means we fail to reject the null hypothesis. And anytime that you fail to reject, if you want to write out the conclusion, you need to begin it this way. You're going to say, there is not sufficient evidence to, and then whatever it is. So in this case, to reject the claim that the mean physics score is 65. Okay? I want to do one more thing here. I want to change. Remember before when I said, what if we had a whole bunch of 90s? So maybe I'll do that. I'm going to change this to a 90 and change this to a 90. And maybe I'll just stop there. How would that have changed things? Well, notice that my mean went up to 76.625, and my standard deviation also went way up, 9.53096. And if that had happened, my t-score would be at 3, way beyond 2. And if that were the case, you would reject the claim that the mean is 65. And you would say that our sample supports the idea that the mean doesn't equal 65, that that's wrong, right? Because we're getting something that would be very unlikely to get if the mean were actually 65. If you have a couple of 90s, you're probably not going to have a mean of 65. Okay, but let me control Z on these. There is a part B to question 1, so I want to go ahead and do that. So let's see if I jump back to the exercise. The researcher realizes that she accidentally recorded the score that should have been a 76 as a 67. Are these corrected scores significant? Well, see, that's the kind of error that happens all the time, right? I mean, we just switched 2 digits. And so the question is, would that be a significant change? So let me do that. Let me quickly change this to a 76. And what changed? Well, as I said, the mean and sample standard deviation changed. So the mean is now 70.25. What do you think is going to happen? 6.47523. We still have 8 data values. We're still leaving the level of significance at 0.05. And if this happened, the t-score would be 2.29, right? So in this case, so let me go down here to part B. Even if t equals 2.29, there is not sufficient evidence. Well, it's the same thing. To reject the claim that the mean physics score is 65. We've talked before, and notice they even do give you a p-value, right? The p-value is 0.055. It's a little bit more than 0.05. I guess if your, level of significance were different, that could change things too, right? So if you change this to 0.01 and you say, hey, I want a 0.01 level of significance, look where the critical values are now. 3.49, right? So in my picture, right, let me go back to kind of show you the difference. When we had 0.05 level of significance on a two-tailed test, that means 95% of the scores are here, and only 5% scores are in the tails. So you would have 0.025 here and 0.025 here, because if you add those up, that's alpha. But what I was just showing you is there are some times that people are going to say, no, we want the level of significance to be 0.01. And if you do that, what's the picture look like? Well, you still have the t-scores, but now we only want, well, we want 99% of the data values to be ones that we accept the null hypothesis, and only 1%, so it'd be like way out here, 0.005, because that's half of 0.01, and way out here, 0.005. This is a two-tailed test. And so what this would mean is you really push those critical values out, and that's what the software is computing. I guess this is rated around 3.5, right? That would be my critical value, and this would be negative 3.5. So only if you were really far away from the mean would you end up in the critical region if your level of significance is 0.01. So I realized that wasn't part of the question, but I thought it might be worth explaining here. Okay. So that's exercise 1. I'm going to skip exercise 2 for this time being, and I'm going to, well, actually, no, I guess that's on, okay, so that's on the next homework. I assigned 3, 4, and 5. 3 is like number 2. I'll come back to it shortly. I think the next one I want to do is problem 4. So we'll work that one out now. So I guess what I want to do here is talk about this formula once again for t. We've said that t is equal to a statistic minus the expected mean of that statistic over the standard error. So again, that's this formula that keeps coming back. I said expected mean, but maybe a better way to say it is hypothesized value. Okay, so here we go. It says in problem 4 that some statistic is normally distributed with an estimated standard error of 12. So they gave me the denominator. So basically what I know right now about number 4 is that the denominator is 12. They also told me that the degrees of freedom is 20. That comes into play. Do we know what the statistic is? No. Part A says, what is the probability that you would have gotten a mean of 107 or more extreme if the population parameter were 100? So the parameter, remember that's this hypothesized value, is 100. And so the question is, basically, if we got 107 or more for our statistic, okay, the question is, what is the probability? So I can draw a picture of this, I guess. We know that the mean is 100. We're saying that the standard error is 12, so it would go up to 112 or it would go down to 88. Those are 12 apart. So the question is, what's the probability of being 107 or more? So 106 would be right in between. So like this area and then this area. That's kind of what we're computing the probability. So the probability of t being bigger than or equal to 107. And then I'm going to do that times 2 because you have the 2 tails, right? And so that's really what I'm computing here. And so we can use the t calculator for this, I suppose. It says you may want to use the t distribution calculator. So I'm going to go ahead and open that link in a new tab. And so I can plug in my t value, right? So my t value, I guess I should use my calculator here to compute it. It's 107 minus 100. That's 7 over 12, okay. Maybe it can compute it for me? No, I think I need a calculator, because I think you really have to put in a decimal for this thing to work. So 7 divided by 12 is 0.5833. I'll put that in for t. 0.5833. And the degrees of freedom I was told is 20. So let's calculate. It says that my two-tailed probability is 0.5662. Okay, so this two-tailed probability is 0.5662, 56% of the area. So a little less than half is in this little hump in the middle. Okay, so that's my answer to part A. Let's look at part B. Oh, there's actually another question. Is this probability significant at the 0.05 level? Well, no. This is a high p-value. It's much higher than 0.05. So I would say it's not significant. Okay, so that's part A. Part B asks me, what is the probability that you would have gotten a mean of 95 or less? All right, so the probability of, well, again, 95 or less. So what are we going to do? We're going to use that same formula, and we're going to look at 95 minus 100 over 12. That'll be the t score. Okay, so that's negative 5 over 12. So let me try doing that. Negative, so let's clear this out. Negative 5 divided by 12 is this decimal. Negative 0.416 repeating, so 0.4167, right? So I can go to the t distribution again and throw in a negative 0.4167. We still have 20 degrees of freedom. And this time, the probability of getting 95 or less. Oh, now that's interesting, because if you look at the exercise, it said it's a one-tailed test. And I knew that because it said 95 or less, whereas the other one says or more extreme. That was a two-tailed test. So the difference is the picture, right, in this problem. So again, the mean's 100. But what we're talking about now is just from 95 over. That's what we're looking at. And so this is not right, because this is two-tailed. Can I change it to one-tailed? Well, I can take that 0.6813, which is the two-tailed probability, 0.6813, and just divide it by 2, because there's symmetry. And so it's 0.34065, right? So the probability for part B is 0.34065. So about 34% of the scores are 95 or less. And so that's my answer to number 4. Number 5. Number 5 is related to number 3, and we'll talk about that in a little bit. So I want to go to number 14 on the homework. And so it says a new test is designed to have a mean of 80 and a standard deviation of 10. And so this is where things are a little bit different now, okay? Because normally we won't know the standard deviation of the thing we're trying to find the mean of, but this is just by design, okay? So it says a random sample of 20 students take the test, so n is 20. And it says, does this score significantly differ from 80? Because the sample mean ended up being 85, so x bar equals 85. Your book uses capital M, but I've been using x bar. It says to answer this problem, you may want to use the normal distribution calculator. And so I have that up here. I'm going to go ahead and launch that here so you can see what it looks like when you do it. But I guess the point is, because sigma is known, we can use the normal distribution. And so I don't need a t distribution in this case. But what I will have is I will write down that z is equal to, and again, it's my statistic, which is x bar, minus, okay, the mean is 80. That's the hypothesized mean, right? Over the standard error. Now the standard error would be 10, well remember it's sigma divided by the square root of n is how this works. And so I guess I'll fill in the rest of the numbers now. So we have 85 minus 80 divided by 10 over the square root of 20. So I'll have to be a little careful here when I use my calculator. Work on this. I have 5, which is the numerator, divided by, and maybe I'll put some parentheses here, 10 divided by the square root of 20. And so when we do 5 divided by that, I get 2.236 for my z-score. Okay, and so when I go to my normal distribution calculator, I want to know the probability that z is bigger than that, 2.236, or z is less than negative 2.236, right? Because this is a two-tailed. So I want to know what's the probability of being outside negative 2.236 and 2.236. And it says that that shaded area is 0.025352. So about 2%. So they didn't say in this problem what alpha is, the significance level. It just says, does the score differ significantly from 80? This is my p-value. It's less than 0.05. So if this is my alpha, then the score does differ significantly. But I guess if they didn't tell you, if it was maybe 0.01, then it wouldn't be a significant difference. So that's the kind of thing that happens. I think on last week's quiz, I forgot to give some of you a value of alpha on your quiz. And you do need that. Confidence intervals and hypothesis testing both depend on this significance level. Okay, so that's the normal distribution calculator. By the way, just to show you, you can do this also on the Google Sheet. I'm just going to show you how you do this. You need to use, right next to the instructions, we've been using sigma unknown for the t-test. When sigma is known, it does the normal distribution. So let me just show you how this works. And if I move over here. We don't need this part. We just need the little calculator. The null hypothesis would be equal to 80 or not equal to 80. The sample mean is 85. Standard deviation is 10. We put in the sample size so it'll compute things for me. Again, I have 0.05. It gives me the p-value, and here's the critical values. So again, the picture is 95% of the area. It goes between 1.96 and negative 1.96. You've seen this picture before. So that means there's another 0.025 out here and another 0.025 out here. 5% is my alpha. So the z-score ended up being 2.23, and so that's in the critical region. And so the p-value would be this area, which is only 2%. But like we were saying before, if you change the significance level to 0.01, now the critical values would actually be outside of 2.23. Okay, that's not what the problem said. It actually didn't give me a significance level, so I guess it's a little ambiguous. But maybe this is helping you understand. That is the point, right? We're trying to learn statistics here. Okay, number 15 is next. So I want to go ahead and work on problem 15 here. We'll take a look. Maybe I can move this over a little bit so you can see my paper. So in 15 it says you perform a one-sample t-test and you calculate that t is equal to 3.0. And I'm going to remind you of this formula we've used again and again, that t is equal to the statistic minus the hypothesized value, so that would be the parameter, over the standard error. So in our example, t is equal to, I've been using x bar, the book's been using a capital M. We've been using mu for the sample mean, and the standard error of the means, we've been using s over the square root of n as an estimate of sigma over the square root of n. So do we have all of these things? Let's see. Well, no, we don't know n. We're trying to find n. We do have t this time, though. That's new. They do tell me that the mean of my sample, so x bar, or capital M, is 1.3. And they do tell me that the standard deviation is 2.6. And what's not clear is what to use for the mean. I'm going to use a mean of 0 here. You will see shortly that there are a lot of situations where that's what we use. But then if I plug into this equation, I now get 3.0 is equal to 1.3 minus 0 over 2.6 divided by the square root of n, okay? So maybe I can rewrite that over on the side here. We have 3 is equal to 1.3, and instead of dividing by a fraction, you might remember that you can multiply by the reciprocal, so I can write square root of n over 2.6. So my equation now says 3 equals 1.3 over 2.6 times the square root of n. By the way, what's 13 divided by 26? That's 1/2. So 3 is 1/2 times the square root of n. And what I'm trying to do, right, in this problem is the question asks how many participants were used in the study. So what you're really trying to do here is find n. I should have been clear about that from the beginning. But I'm trying to get the n by itself. So just doing a little algebra, I will multiply both sides by 2. So now I know that 6 is the square root of n. And if I square both sides, I can get the value of n. N is equal to 36. So problem 15 was not an easy problem. And you may be wondering, why do we use mu equals 0? And I am about to go back to problem 3 to show you another example where using mu equals 0 makes perfect sense. Okay, we're going to go back to problem 3, as you can see on the left. And they give you a chart of vocabulary tests for 20-year-olds and 60-year-olds. And the question says we're supposed to test the mean difference for significance using the 0.05 level. And they give me a link to the relevant section. And then we're supposed to list some assumptions made. I'll let you look those up yourself. But if we click on the relevant section, difference between two means and independent groups. They're talking a little bit, but here's our familiar friend, right? So I wrote that up here from the last problem. T equals statistic minus hypothesized value over the standard error. But the trick is, what is the statistic? And they're calling it M1 minus M2. I guess I'll do that also. So we have M1 minus M2. I gotta be careful, those M's start to look like mu's for me. Okay, so we're interested in the difference of those two means. Now what do we hypothesize the value is? Well, the hypothesized value, I guess I could call mu1 minus mu2, the mean of the first, so to say the mean of the 60-year-olds and the mean of the 20-year-olds, right? So what I really need here maybe is to copy this chart down from the homework. Let me go back to the homework problem. So we have this chart, right? So maybe over on the side I should have my 20-year-olds and my 60-year-olds. Okay, and I could start listing those out. And of course, you know, we have technology, we'd like to use it. Maybe I'll go back to my copy of my hypothesis test. Maybe I'll go right to the instructions page, which is pretty much a blank page. What I'm going to do is I'm going to see if I can copy this data from the exercise onto my Excel spreadsheet. I'd really like to be able to do that. So let's see if that works out. Well, there it all is, but it didn't copy exactly the way I wanted. Let me try one more way of doing this. So if I maybe copied all except for that last one, so there's 9 in one column and 8 in the other. Maybe this will work. So if I copy the 9 in one column and 8 in the other of the other one, well, let's copy 8 and 8 plus the labels. So then probably go here. There they are. And then I just need that extra value there. So what was that? That was a 13. So I'll put that here. And of course you can change the formatting, you can center all this. Let's align it all in the center. Let me move these labels up higher. I don't really need those. That's not data. So I guess my point is that we can look at these things separately. We can compute the mean of the G's and we can compute the mean of the H's. So maybe that's the thing to do is, you know, if I compute the mean of those, so let me go to where we were before. So now there's 9 data values and the mean is 19.22. So maybe I'll label that M1 is 19.222. But over here I'm going to have M2. And I'll label what that is. I guess the sample standard deviation may come in handy later. So I'll copy that down, and I'll even copy down the fact that there's 9, whereas over here there's only 8. Let's get what that mean and standard deviation are. So again, on the instruction page, I had copied all the scores of the 60-year-olds. And I'll go back. Let me clear these out and paste them in here. There's 8 values now. And so their mean is 25.375, and their sample standard deviation is 4.80885. Okay, so I have those things. Those are not. those are values that may come in handy as I work this out. And we're going to do a little of the work on paper. So again, the way this works is we take m1 minus m2 minus mu1 minus mu2 over this standard error. So this is going to be a little bit tricky. We'll get to there in just a second. It will be easy for me to do m1 minus m2. I can actually do that right now if I wanted. m1 minus m2 is, well, we have to subtract these two values. So I could do that right on the paper if I want, right? I could say equals this minus, which is 07 minus P7, and it'll subtract, and it'll tell me that the difference is negative 6.153. So when I get to the next step, on the paper, it's going to say T equals negative 6.153. Now, next we're supposed to subtract mu1 minus mu2, and you might be wondering, what is that? Well, that's the hypothesized value. So again, when you do a hypothesis test, you have a null hypothesis and an alternative hypothesis. And the null hypothesis is that the two means are the same. Or maybe we have enough evidence, let's look at this chart again. Maybe there's evidence that one group scores better on vocabulary tests than the other group, and then so that would be the alternative hypothesis. So we're trying to figure out if we would reject the null hypothesis. So you put the hypothesized value here. Well, here's the thing, guys. If mu1 were to equal mu2, you could subtract mu2 from both sides, right? And if you did, you would get mu1 minus mu2 on this side, and you would get 0 on that side. So here's another example where the hypothesized value is 0, and this is not an uncommon occurrence. Now, I guess what is uncommon is figuring out what to put for the standard error. It's not as simple as s over square root of n, like the last one we had. So I want to go to the relevant section to kind of show you what happens. So they talk a little bit about this standard error of the difference of the means, and it was the square root of 2 sigma squared over n. We've done this before, but you may not remember that one. And then we have to, since we don't know sigma squared the variance, we have to estimate that using this formula. So that's what they call the mean sample error. Okay, it's an estimate of sigma squared. And now, because of the fact that we're in a special situation where the number of data points are different, we're in this special section here at the bottom, computation for unequal sample sizes. Well, the MSE estimate of the variance assumes that you have the same number of people in each group, but when you don't do that, you need to compensate for that using this sum of squares error. And then the MSE is computed by the sum of squares error over the degrees of freedom. So maybe I'll write some of that down. so I don't forget it, right? So this is what we're going to call MSE, okay? Or another way to say it is it's SSE over the degrees of freedom. And up above, they tell me how to compute the SSE, and down below, they show me how to compute the degrees of freedom. Degrees of freedom actually isn't too bad. It says the degrees of freedom is n1 minus 1 plus n2 minus 1. So if you go back and look at our data, in our example, we had 9 minus 1 plus 8 minus 1, right? So that's 8 plus 7, that's 15. So we're going to be dividing SSE by 15. So I guess I have a little bit of work to do to figure out what SSE is. And I can go back to my testing a difference of means. And so they say we're going to add up the difference from the first mean squared plus the sum of the difference from the second mean squared. So this is kind of interesting. We can go back to the original data. And so it turns out that these means are going to be coming in handy. So that 19.222 and that 25.375, I'm going to go ahead and copy those onto the very front, because we actually don't have a nice worksheet for two variables. I'll just put those there so I can remember them. And so, again, the way you do this, maybe I'll move these 60-year-olds over here. I'll put the mean of the 20-year-olds right here, and I'll put the mean of the 60-year-olds right there. Actually, I'm going to move it over one more column. Oops, did that a little too fast. So let's see if I take all these values and move them over just a little bit. That'll help. Okay. So what I want to do in this column is I want to do what this formula says. We need to add up x minus m1 quantities squared. Okay, so watch how this works. When I go back to this hypothesis test, I'm going to say this equals this data, 27, minus this data point. Oh, but I want to square that, so I'm going to put that in parentheses. And the way I square it is to write a caret 2, and there we are. And if I just had this value copied over and over again, now if I copy this formula to this square, it'll, no, that's not quite what I want, is it? So we'll try again. If we copy this formula to this square, notice the number's different because now it's using these two values, g and I. And so this is a way of very quickly computing all of these sums of the deviation from the mean, you might say. So we're getting the SSE shortly. I'll have to do something similar here. So I'm going to move this over, and I'm going to copy it and put it right here so that I have the 25.375 ready to go. I think if I copy this one and put it into that square with the k's, that's not what I want. I want to get that formula there. So this did not work. Oh yeah, it did. It's a very small value. 26 is very close to 25.375, But if I copy that value all the way down, like 16 is going to have a lot of error. And so sure enough, that's 87. Okay. So basically what I need to do now is I need to do a lot of adding. Okay. So down here I'm going to have SSE. And the way I'm going to do it is I'm going to add the sum of, well, all of these values plus the sum of all of these values. And that 409 is my SSE. So yeah, this was a tough problem. What do we do with the SSE again? Oh yeah, it's in the formula here. So now I need to get this denominator for t, right? So right now, what I have is t is negative 6.153 divided by, it's supposed to be SSE divided by 15. I may as well do that on the calculator as well. So let me put equals this divided by 15. And there's my 27.2. So I have 27.295. And so let's figure out what my t value is, right? Equals negative 6.153 divided by 27.295. And I got negative 0.2254. That's my t value. And once I have my t value, I should be able to compute the probability that they're asking for. Let's take a look. So if we go back to the exercises, let's get that. Here we go. So let me be clear here. This is not MSE. We need MSE to compute it, but again, this is the standard error. So we could write this as the standard error of the difference of the means, right? And so the standard error of the difference of the means comes from this, but that's not the exact formula. So this 27 is not right. Okay. So in the book, they tell me that it's S of m1 minus m2 is the square root of 2 times this MSE divided by NH, the harmonic mean. What is the harmonic mean? Well, they tell me it's 2 over 1 over the first sample size plus 1 over the second sample size. Now in my case, those were 9 and 8. So this is 2 over 1/9 plus 1/8. And again, a calculator can help me figure that out. So I guess there's a little more work to do here. We'll go back to the calculator. Okay. So I'm going to call this n sub h. That's the harmonic mean. And that's equal to 2 divided by 1/9 plus 1/8 is my denominator. Okay, so we have an 8.47 for the denominator. And now, since that's my 8.47058, I can take that value to compute this standard error. So, S, my standard error, I'll put that here. That's going to be equal to the square root of what? Well, they say 2 times MSE. 2 times. Now the MSE we already computed. The MSE was the SSE divided by the degrees of freedom. So I'll say it's 2 times H16 divided by the degrees of freedom. We worked that out already. That was 15, right? Okay. And now we want to divide by this value up here, which is the harmonic mean. And so there, that is what S is, the 2.538, or 2.539 if we round. Okay, now I'm ready to get my t-value and finish the problem. Negative 6.153 divided by 2.539 equals, and let's see where we're at. 6.153 divided by 2.539. So actually, let me write that down here. T, and that equals negative 6.153 divided by 2.539. Negative 2.4233. Okay, so that's my t-value. And the question is, if that's my t-value, what is the probability? And of course, we have t calculators that we've used before. So I could try this. I could try negative 2.4233. And it asks me for degrees of freedom. We said that's 15 in this problem because we worked that out in the middle of the thing. Calculate. And it says that my two-tailed probability would be 0.0285. So my p-value I could write is 0.0285. And so we might say this is a significant difference. And so I guess I should really go back to the problem and see what it was asking again. Test the mean difference using the 0.05 level. And I'm going to say, yeah, there is a significant difference between the vocab test scores of the 20-year-olds and the vocab test scores of the 60-year-olds. I think these 29s kind of set us over the edge. So we would conclude there is a significant difference between the groups. So you might start to suspect that maybe 60-year-olds have a higher vocabulary than 20-year-olds. But you could see two things from this example, or maybe three things that I want to emphasize. Number one, it's ugly to do some of these computations. Can you imagine if I didn't have a computer? You can see why I want you guys working hard to get more comfortable using the computer. Number two, even though I am using the computer, it's important to write things down, because only by writing things down can you see that I really am doing the same thing I did with one population. Here's two populations, but it's still statistic minus hypothesized value over standard error. It's just that the formulas get more complicated. And the third thing was that quite often we will assume that the means are equal. That's the null hypothesis, and that's why you get a 0 here. So if you have questions, please ask. But I can tell you that when you go to try number 2, and there's a hypothetical experiment going on, 10 subjects are each tested twice. Well, I can tell you it's going to be similar to this, although we're at a different section. The relevant section, these are called correlated pairs. Why? Well, because if you go back to the problem 2, and we skip this one, that's for Friday, everybody here is having 2 glasses of water or 2 glasses of alcohol, right? Are you given the alcohol first or the water first? And then how do you perform on the motor test? And the point is, it's the same people, so these scores should be correlated. Some people seem to have no effect. Some people get very high scores all the time or very low scores all the time, right? So it makes sense that the first column and the second column are very related. Whereas problem 3, 20-year-olds and 60-year-olds, these means should really be independent because the groups really don't have anything to do with each other. So I guess the point is, when you go to hear difference between 2 pairs, you'll have to read a little bit, but the formulas are going to be a little bit different. And so the standard error formula comes from this law, and so they tell you that it has to do with R, the correlation coefficient. And so, anyways, maybe you can use this to help you work through problem 2. So as I look at the rest of the homework problems for Friday, there's a lot here. If you found what I just explained to be difficult, maybe you should pick and choose a little bit. For example, maybe question 13 would be a good one to start with. I mentioned question 2 is different than what I just did, but question 13 is the same. You're calculating a t-value, and then it says, are the mean test scores of these 2 groups significantly different at the 0.05 level? And then it says, what would the t-value be if there were only 6 participants? And remember, they give you answers sometimes at the bottom. So problem 13, for part A, they say that the t-value is 2.57. And that was 22 degrees of freedom because there were n-1, n-1 is 11 plus 11. So again, question 13 is very similar to the problem 3 that we just worked through. You can kind of follow it word for word if you want. If you're looking for another one that's kind of like that, I'll draw your attention to problems 8 and 9. In problem 8, people are throwing darts at a target. These would be correlated pairs, right? I mean, someone that's very good at darts might be able to do it either-handed. Someone that's not very good at darts might not be able to do it at all. But look at question 9. Assume the data in the previous problem were collected using 2 different groups of subjects. One group used their preferred hand and the other group used their non-preferred hand. Analyze the data and compare the results to those for the previous problem. So again, problem 9 would also be a nice problem that could be done that is like problem 3. So if you want to work some of these out, at least you now have a template for some of them. For the other ones, you'd have to read a little more. I do not plan on testing you on everything on the quiz. I'll give you a little more detail on exactly what you need to prepare for the quiz. Yeah, there's a lot in this chapter. So I'll give you a little more detail shortly.